So today onwards, we start our next module in this course, which is discussion on input-output management. So as we've already discussed in the course, that the three primary goals of an operating system is management of processes, management of the memory, and management of the input-output devices. So this third module is all about understanding how the input and the output devices are managed by the operating system. But before we go into the details of the understanding of how OS manages the input-output devices, we first will look at the structure of the device, the different kinds of devices that are managed by the operating system. And we'll also talk about a bit about how the devices interact with the CPU. Now, this is important because until you know how the devices interact, will not be able to understand how the operating system manages them. So today's lecture will primarily be focusing on understanding of the different devices. When I say devices, I mean the input-output devices, and how they interact with the CPU, how the data is transferred between devices and the CPU. So this is what we are going to discuss about today. And in addition to that, we'll also talk about the interface with which the operating system manages or tries to interact with these devices. And this interface is what we call the device driver. So I'll introduce you to the concept of device driver. So let's move on with first the idea of what are the different input-output devices that interact with the CPU. And the slides that I'm showing you in this lecture is from Rutgers University. The author is already mentioned, so acknowledgements, and I would like to thank the author for providing the slides which I'm using for this lecture. Okay, so by this time all of you are aware of the entire structure of a computer system, right? So we have already seen that when we think about a computer system, the first component that comes to our mind is the computing unit, which we usually call the CPU. Now, this computing unit is supposed to execute instructions as provided by the user, which are stored in something called memory, and they are stored in different locations of the memory. CPU reads them and executes them. We've already seen that how operating system manages this memory in storing different kinds of processes. So these two components of a computer system, they interact. Well, OS handles this problem. But there are several other things also that are connected to this CPU. And they are the ones which provide the data. They are called the input unit and the output unit. So this input and the output units are the ones that help in providing the data to the CPU. So they are the ones that are connected to the CPU. Okay. So if these are the systems or these are the components that are connected, they must also be managed. So here comes another goal of an operating system, managing these devices. But this is a far more challenging problem than handling handling the processes or the memory, because these devices are of different types and they deal with different kinds of data. So the problem is far more challenging. So as you see here, we are first going to list out the different kinds of devices that are connected to the CPU, because it's important to know the nature of these devices. Only then one can understand how the data that is stored in them can be managed. So if we try to classify the different devices that are connected to the CPU, they can broadly be classified into three categories. The first, which are called block devices. So as the name implies, the data that is stored in these devices are obtained as a group. They are obtained in bulk. So that's called a block. Example are the disk drives, the hard disk that you use in your computer system. They are block devices. We will talk about the structure of them in details. So for the time being, let's try to understand that they are a kind of block device where the data, you cannot obtain them as one single byte or a word. You obtain them as a group of words. So it's called an entire block. Minimum, you see, when you will be accessing one data unit of a block device, maybe for example, in a hard disk, the minimum that you would be able to access is 512 bytes. Okay. So in one memory access, in one disk access, you will obtain 512 bytes. So that's a block of word. Flash memory, which we frequently use for storing data, the pen drive that we normally call it, they're also block devices. You obtain them as a group of words. Okay? And this entire block, interestingly, is an addressable block. That means if you will be sending out an address, or the CPU sends out an address to obtain a particular byte, in addition to that byte, you actually get an entire block. The byte residing in that particular block, you get the entire block. And as you know that this phenomena is very, very suitable for implementing the cache mechanism, where the idea is that in addition to the one that I'm currently accessing, I would also bring all the addresses that are lying near to that currently address, the current address. And because in all probability, the addresses that will be, would be accessed next would be the ones which would be closer to the currently the current address. So its advantage is that in addition to the current address, you bring all the addresses that are near to that. So the data of all the addresses near to it. This is the basic idea behind block devices. Okay. The second category of devices are network devices. Examples are Ethernet, wireless network, and they are devices which provide data in the form of packets. And what are these? The data is divided into small units, and these units are called packets. Now, interesting thing about this transfer of data, this kind of transfer of data, is that your entire data, say for example, I have 1 kilobytes of data. Now this 1 kilobytes of data will be divided into number of chunks of, let's say, maybe 64 bytes. Each would be of 64 bytes. So 1K by 64, these many amount of chunks you will have. And these chunks will be called packets, right? So one by one. So you won't send that entire 1 kilobytes of data. You will first send this one, then this one, then this one, then this one. And interestingly, they will follow the same path. Okay. Now, why do you do that? Well, the medium through which this particular data transfer is going to happen only allows data of size 64 bytes. Let us assume that. So I can't send the entire 1 kilobytes of data. I have to send only 64 bytes, but I have to send the entire information, which is in 1 kilobytes. So I divide that into chunks of 64 bytes and I send it. And in addition to the 64 bytes, I add some additional bits on the two sides of that, which are called the header and the tailor information. And they will keep some additional information regarding the path through which that particular data should travel. This is called the network information. So this kind of data transfer is what we call the packet-based data transfer. So devices, which we call network devices, they follow this kind of data transfer. This is the second category of devices that we usually deal with. The third kind of devices that we come across are character level devices, where data is transferred in the form of characters. The usual input-output devices that we operate, the mouse, the keyboard, these are all devices that provide data to the CPU in the form of a specific size, 8 bytes or 1 byte or 2 bytes, whatever. So it's a byte level data transfer. Say, for example, an audio, keyboard, mouse. So there, the data is transferred in the form of bytes. We call them byte streams. Okay. So whether it is a block device or a network device or a character device, all these devices finally are connected to the CPU. Just the amount of data that they transfer, that varies. Some send only 8 bits, some send 4 chunks of 8 bits, some send data a voluminous data of a larger size. But whatever be the amount of data that gets transferred between these devices to the CPU, it has to be through some communication medium. Okay, and the medium through which they communicate is what we call the bus. What is this bus? It's a collection of wires, that's all. Some wires that are connected from the CPU to the input-output device. We've already seen a kind of bus which connects the CPU and the memory. We call them the address bus, the data bus, the control bus. Address bus to carry the addresses from the CPU to the memory. Data bus to carry data from the CPU to the memory or from memory to the CPU. And control bus is to send the read or the write information to the memory. So there is a kind of connection between the CPU and the memory. It has to be. There has to be some kind of connection. And we call that particular connection as the memory bus. So similarly, the input-output devices are also connected to the CPU via some kind of communicating buses. And this is how these devices send signals to the CPU or receive signals from the CPU. Okay. Now, when we were talking about memory management, you must have seen that the basic idea of managing the memory was how you can accommodate a number of processes within that fixed size of memory. This is what the challenge was. Okay, so this was the challenge, that there will be a number of processes that the CPU would want to run, but they have to be accommodated in the memory. Sometimes there may not be sufficient amount of storage available, but how the OS manages that, that is all about memory management. But the problem of memory management was restricted to when the particular system is working. That is, we know that the data which resides in the memory is alive or it's needed as long as the memory is working or the system is power on. The moment we turn off the power, everything that is stored in the memory gets lost. Okay, it's a volatile memory, so everything gets lost. So all processes, they are either they terminate normally or they abruptly they terminate. But here we have a situation where we want to store the data persistently, permanently. And that is the reason why we have different kinds of devices which would be storing the data permanently. So this is a far more challenging problem because you have to think about how to keep that data within that persistent storage. And at the same time, you have to understand how will that be perceived by the CPU. Okay, so we'll understand that as we proceed in the chapter. But first, let's talk about, we just saw that the devices that will interact with the CPU will be of different type. They will have different kinds of data that they will deal with. Okay, so how will the system recognize these devices? Please try to understand. Devices are of different type, but you want one, when the CPU will look at these devices, it will have one common way of addressing every device. And this is what we have been calling as abstraction. We have seen the concept of abstraction while dealing with processes. We saw the concept of abstraction while dealing with memory. If you remember, when we introduced the concept of virtual memory, the idea was that wherever the process may reside in the physical memory, it's not of my concern. When I will be sending out an address, I will assume that everything is there in one place. And this was the concept of virtual memory, which was again an abstraction. Actually, the thing is distributed in the physical memory, but when I am sending out an address, the CPU is sending out an address, it feels that the entire address space is a contiguous address space. This is the abstraction that was introduced. Absolutely same thing happens here as well. The devices can be any. They can deal with any kind of data. But when they will be the mode of access, that should remain same for all the devices. How will that be ensured? And this is what the OS addresses. Okay, so the first thing that one should understand is whether you are dealing with a character level device or you are dealing with a block level device, whatever be the device you're talking about, character level or block level, these devices will appear in the file system namespace. There are two things that we have introduced here. We'll come across this in more details as we proceed in this chapter. For the time being, let me just introduce you to these two terms and I'll explain that later. File system is a way of organizing files. What is a file? File is, you can say, some kind of a way to represent data in a persistent way. We just saw that data, when we work with program and data, they reside in the memory. But that's as long as the system is powered on, you work with these temporary data. But the moment power is turned off, the data that is residing in the physical memory, that is lost. So in order to save that permanently, you don't need to store it in some persistent storage, right? And you need to store that data in some other device to hold the data permanently. Now, the way to organize that or way to store that data in such kind of persistent storage is called a file. So, simply put, file is nothing but an array of bytes. For the time being, let us try to define it in this way. It's an array of bytes, which is some kind of representation of a data. Some data is what we have generated, and that data is represented in the form of an array of bytes. And this array of bytes is stored permanently in some devices. Okay. Now, several files can be generated. Hundreds and hundreds of files can be generated. But you have to organize these files. Why? Because if you don't organize them, then we cannot perform any operation on them. What kind of operation do we perform on files? There are very common operations such as searching a file. You want to open a file. You want to read from a file. You want to write to a file. These are the common operations. So if you have lots and lots of files, you need to properly organize them so that you can perform the operations in a very organized way. It's very easy for you to perform the operation. So in order to organize that, you need to follow some rules. So file system is nothing but an organization of files. We can put it as like some kind of organization of files. What organization are we talking about? Well, structuring them or putting them in an ordered way, keeping them in an ordered way, some method you find out by which you can keep them in a structured way so that you can perform operations on them easily. What organization are we talking about? Well, the organization that we usually follow is the method, or we use something called directories. What are they? And they are also files, but they contain information about other files. They don't contain data, but they contain some metadata. So directories are also files, but the content of these files are metadata, that is information about other files. That's the difference between a file and a directory. Directory is a file that contains information about other files. So file system is kind of an organization that makes use of directories to structure the files. Okay, more of that will come later. So as we mentioned here, that these devices, the character devices, the block devices, they are also treated as a file. So that means they also form some part of the file system. File system is nothing but organizing your data in the form of files and directories. So if you are working with a certain device, the device will also be treated as a file and will be part of the file system namespace. Namespace means the name that you give to every file. Similarly, you also give a name to every device. And when you try to access a device, you actually access a file corresponding to that device. That is the reason why the title of this slide is Devices as Files. So how does the OS look at a particular device? It looks at a particular device as a file, as an array of bytes. So it's like this. Suppose there's a device called D1. That's a device that is attached to the CPU. But suppose this device has to be accessed. Now this device, suppose this is the kernel, okay, and there is an organization of files within the kernel which keeps track of which are the files that is currently present in the system, whether that file is currently open or not. Similar to that, the information about this device that is attached to the CPU is also maintained in that file system. And there is a file corresponding to that particular device. So whenever the kernel wants to access the device, it will actually access the file corresponding to the device. And all operations that will be done on that particular device will be done by the OS on the file corresponding to the device. This is the basic idea. So that is why I'm saying that on one side you have a physical device that is attached to the CPU, and on the other side you have an abstraction of that device created for the OS. So the system looks at that particular file, the device, in the form of a file. Okay. So whenever the system wants to read or write to a file, or sorry, read or write to a device, it is equivalent to reading or writing to that particular file maintained by the kernel within its file system. So see, if you treat the device as a file of the file system, all the operations that you can do on the file are equally applicable for the device as well. So things become very simple. This is the abstraction that we create. So all the operations like open, close, read, write, they are performed on the device. So in addition to that, you may have some extra control, which is device specific, because we just saw that every device is different. Every device has a different way to deal with the data. So there can be some device specific functions, but overall, this is how a file is handled or a device is. Okay. So once we get to know that, okay, this is how the devices are and this is how the devices work, let's talk about how the devices interact, because only then we'll be able to understand how the OS handles the devices. Now, when we talk about devices, something that should be made clear to you, you must have gone through that in your computer organization and architecture course, but still, let me quickly refresh your memory. Now, when we say device, input and output device, let's assume that this is a device, maybe an input device or an output device. And this is the physical device, a keyboard or a mouse or a printer, whatever you call it, input or output device. That's the physical device, the electromechanical part that you attach to your computer. Okay, that's one side. But what the system views, okay, this is the CPU, the processor that would actually obtain the data from this device. Now, they don't interact directly. There is a middleman that is sitting in between the two, and this is called the device controller. Get this thing very, very clear. This is called the device controller. What is this? It's a chip. It's a hardware. So for every device, you have a device controller. These two, this is the device and this is the device controller. Usually, this is part of the motherboard. Okay. So every device will have. If it is a keyboard, the keyboard will have a device controller. If it is a mouse or the printer will have a device controller. So every device will have a device controller. It has to be. It's a hardware. Okay. Well, so the interaction between the CPU and the I/O is through this device controller. On one side, the device controller is attached to the input-output device, and on the other side, it is attached to the CPU. Clear? So it's kind of a middleware that is sitting in between the input-output device and the CPU. So suppose this input or output device now needs to be accessed by the CPU. The flow would be through this middleware. And it will be like this. The CPU will be instructing this or sending out some instructions to this device. And in turn, this device would trigger this physical device, either for reading purpose or for writing purpose. We will see the different steps in doing that. But overall, this is the picture. Every device, whether you are talking about a keyboard or a hard disk or a mouse or a printer, for each one of them, you will have a chip which is there. That's the hardware controller. So the interaction between the CPU and the device is through this hardware controller. Clear? This is the big picture view. I'll detail out everything, don't worry. Okay. Now, when we say that, okay, the CPU is planning to access this device, what it should do is, it should send out some info or some instructions to this device controller. And sending instructions to this device controller is what we call programming the hardware. Programming the hardware or programming the IO, whatever you call. Programming the IO means you are sending out some instructions so that the device can be read or the device can be written. This is the idea. Every device will have its hardware controller, which will be interfaced to the CPU, and the CPU will be interacting with it. How will this communication happen? Well, there are some standard procedures. I'm going to come to this. For the time being, just try to understand that there are every device. When I say device, I will henceforth be mentioning the device controller, because this is not important to me. What is important is this one, the device controller, because this is the one which actually gets programmed. So I should know what is there inside this device controller. Is the flow clear to everyone? Please, this picture should be very, very clear in your mind, that every device that you connect to your computer has a device controller associated, which is interfaced with the CPU. When the CPU wants to interface to the device, it actually interfaces to the device controller. So what is there in the device controller? Well, there are some set of registers which are there in every device. We usually call them command registers. Every device controller has some standard registers, and these registers are for different purposes. What are the common registers that are present in any device controller? The first one is where you use a register to know the status of that particular device, whether the device is currently in use or it is free. So this particular register tells you the state of that particular device. So CPU reads that state and knows whether the particular device is free or it is in use. Then there is the lines for the data to be sent, the ready, the read, the write, all these. But primarily there are three kinds of registers that are there in any device. One that gives you information about the status of the device. Two, that receives some commands from the CPU. And three, the ones that send the data in or data out. So these are the primarily the three type of registers that are there in any hardware. The status that tells the status of that particular device, the command that receives the command read, write, whatever, and third, the actual data that has to be transferred. These are the three categories of registers that are there. Okay. Now, so these registers are where? Well, these are here in this device controller. Here you have these three kind of registers. So let's say this is a keyboard. The keyboard has to be programmed. So it will have the command status register, the command register, the data register. The CPU will first program that, and then whatever data it wants to send will send into this data, and this data will be read by this keyboard. Or if it is keyboard, it will be other way. Sorry, it will be other way. So let's say the keyboard is the input device. So input device means the data will flow from the keyboard to the data, then to the via the data bus to the CPU. And prior to that, there will be the status and the command, which will be read by the CPU to check. Status will be read by the CPU, command will be sent by the CPU, and then the keyboard will be sending the data. This is the way in which things interact. Okay. Now you may wonder, well, you are saying that there are registers within the device controller. This is the keyboard controller. Fine. But how does the CPU send these instructions? How does the CPU access these controllers? How does it do that? Well, it does it through some instructions. What else? CPU has nothing else to do. There are some instructions that are sent to this. But what do you have in these instructions? What kind of instructions are they? They are very, very similar to the instructions that are sent to the memory. What are they? Well, they are kind of a load and store kind of instructions. These are the most common instructions that are sent for reading and writing to a memory. Exactly the same thing is done for input output as well. But you may ask, sir, but you said that these are for memory. But these are not memory devices. So how can load and store be used? Well, idea is, what is the operand for a load instruction? Some address. What is the operand for a load store instruction? Some address. What does it mean? If I say, okay, load to 2000 hex location, it means load something to the memory address number 2000. And it understands, okay, memory location 2000, there you load something. Or load from this, read from there. Store something to 2000 means store something to this location. Can we use the same principle for accessing an IO? Yes. If this address would have been an IO address, I would have done the same thing. That means if I treat an address of an input-output device same as that of memory, I can send out the same kind of instructions as I would have done while accessing a memory. The process remains the same. And this is exactly what is commonly referred to as memory map. The name itself, it means the device registers are mapped into memory. Means these registers that have to be programmed for a device controller, each one of them will have an address, and that address will be very similar to an address of a memory location. So suppose I am writing load 2004. Now instead of 2004 meaning a memory address, it will actually mean one of the registers of one of the device controllers. That's it. So this is this kind of accessing of IO, where the IO registers, the address of those IO registers are treated as if they are memory locations, is what we call memory map. And as you see here, the device registers are mapped to memory locations. Standard memory load store instructions, they can be used to interface the device. It becomes very easy. You don't have any changes to make. You don't have to introduce any new instruction. Same instructions can be used to access both IO as well as memory. Yes. Problem is, how will you know which address to be used for memory, which address to be used for IO? There will be a separation. We will be deciding that, okay, this range to this range will be for memory locations. Addresses after this will be treated as registers of IO devices. This is the basic. Okay, let me show you the system architecture. Is it visible?
Yes, sir.
Okay. And this is the picture that I want all of you to understand. This is the CPU, memory, and memory bus. So we are all aware of this. We already have seen. Okay. What is interesting is the lower half of the figure. As you see, the buses are not only the ones that connect the CPU and memory. The buses, there are also two kinds of buses that connect different other devices to the CPU. For example, here we have a graphics processor, a graphics unit that connects it to the CPU. And this bus, as you see here, it's called the PCI bus. That's one kind of bus, a high performance bus. And if you go further below, you will see that there is also some other kind of devices, SCSI, SATA, USB. They are also connected to the CPU via another kind of bus. They are called peripheral bus. Now, the interesting thing that happens here is that the graphics devices, they are connected to the bus, which is very, very high performing. And as you see, they are closer to the CPU. Okay, they are closer to the CPU. Because if you want a very high performing bus, you cannot have that farther away from the CPU. It has to be closer to the CPU. Whereas if you have the more voluminous data transfer, such as the SATA hard disk or the USB drives, they generally use different kind of bus, which is called the peripheral I/O bus, and they are relatively low performing. So this is overall the picture of the different devices. Okay, let's look at how the modern system architecture works. I've already told you about that. It's just another view. As you see, the graphics unit is connected to the CPU via PCI bus. And today's chips are sophisticated, where they include some additional I/O chip that acts as a hub. And all the low-end performing devices like the hard disk, the keyboard, the mouse, they, instead of directly connecting via the bus directly to the CPU, they connect themselves to the I/O chip. See a figure that is written I/O chip. All of them get connected to this I/O chip, which is nothing but it's kind of a hub, a DMI interface, and that in turn gets connected to the CPU. Look at the figure, the lower half of this figure. We have the network that connects itself to the PCI bus, but that PCI bus does not directly take it to the CPU, it takes it to the I/O chip. The keyboard mouse gets connected to the I/O chip. The hard disk gets connected to the I/O chip. And the I/O chip in turn gets connected via a DMI interface to the CPU. So this is what happens. Okay. Good. Now, let me be more focused. And I have already discussed about that. This is why I thought I would show you this particular figure, because this is a more generic idea. So what the figure that figure 36.3 on this PDF is showing you is the generic idea of how a hardware controller or I/O device, whatever you call it, that is interfaced to a CPU. What is it? We have written it as a canonical device. It consists of some registers, status, command, and data. I've already told you about that. And this is basically the interface, the software interface, which the system uses to communicate. Let's have a look at this. So from figure 36.3, we see that a device has two important components. The first is the hardware interface, okay, and second is the internal structure. Internal structure means depending on what and how complex that particular hardware is. That hardware controller may have a microcontroller, it may have an onboard RAM, it may have other hardware chips, but overall the picture is this. Okay, right. So this is, we understand that hardware controller is this. Now let's look at the protocol, how the interface happens. Now I'm spending this amount of time to make you aware what goes on at the lower level, because until you understand that, you will not understand the concept of device driver. And if you don't understand device driver, it will be very difficult for you to understand how file system is handled. Because at the lowest level, this is the operation that goes on. What we are going to talk about maybe in the next lecture or in the next to next lecture is we'll talk about the abstraction which is sitting on top of this. So you have to understand what is going on below so that you appreciate how the abstraction is created. Okay. So this is the picture that should be clear to you. We have a device, we have a device controller, we have the device is a physical device. It works in its own way. It cannot be directly communicated to the CPU because every device is unique. Every device has its own way of data transfer. So the one that actually gets, which interfaces to the CPU is its hardware controller. What is there in the hardware controller? Some set of registers, status command and data, and maybe some microcontroller and some additional circuit. Overall, this is the structure. Now let's talk about the protocol, how the thing works, how does CPU interact. Okay, it's like this. Let's have a look at this, the protocol that is shown in as a code. So what is the idea? The idea is that you have first a check of the status. While status equal to busy, that is the particular device. If the device is busy, its status register will signal a busy. Okay. So when the CPU will read the status register, it will find that the device is busy. Take for example a printer. One process is currently printing something. Some print job is currently being run or executed. So if one process is currently printing something, the other process cannot use the same printer. So when the second process will be executed by the CPU, its first job would be, before it starts printing, it will check the status of that particular device. And when we read the status register of the device, it will find that it is busy because already one other process is currently printing. Okay. So while status equal to busy, it loops, right? Okay. Assume that the status is not busy. If the status is not busy, then what do? You write the command to the command register. Just go to the third line. What command? Well, there can be different kinds of commands. For example, we just saw that all the load and store kind of instructions can be utilized for IOs as well. So any command that you would like to do, read or write, put that in the command register and send the data. This is the simple protocol that we have. Okay. Right. Yeah. Let me come back to slide once again. Any questions so far? Is it clear to all of you? Okay. Let me quickly wrap up this whole thing. So the idea is like this, that we have here this is the host. We may call it the CPU that is running the operating system. So I will write it as like, this is the CPU that is running the kernel. And here we have the device controller. So let me write it as device controller. I'm using a more generic term. I'm not referring to any specific device. And this is the device that we have, the physical unit, input or output. Well, let me, for simplicity, take an example of the hardware, disk controller, the hard disk, right? So as we know that the hard disk is nothing but a block. Hard disk is a block level device. So whenever you would like to access some data from a hard disk, you have to mention the data in the form of a block. which is the block number that you would like to access. So let us look at how the abstraction would, or how the flow would be performed. So here we have the host. The kernel would put the block number, let's say it's a block device. So let's say the kernel puts the block number and puts it into the data output line. So let's call this as the data line that goes on to the device. And here we have the command register. Okay. So the kernel, in addition to that, it puts, say, some kind of a read operation. The operation that, or the command that it wants to convey. This again is taken to the device. Okay. And in the meantime, before this entire thing happens, so this is, say, it's ready, and this has been read by the CPU. So the device has put the status to this ready, which has been read by the kernel, and accordingly it has put the value of the command in the command register and put the data, which is the block number. So the block number is transferred to the data register, which in turn is sent to the device. So this is basically the interface that is there. And when I say this read, I'm actually mentioning that though I have read it as read or write, you may assume that these instructions will be something like out byte or in byte followed by an address, and that address will be the address of the register. So this is the interface, the mechanism through which data moves in and out of the device. Okay, right. Okay, so this mechanism of reading in and reading out data from the device controller to the CPU is what we call programmed I/O. Okay. It's called programmed I/O. We have already, I've already told you that this is a program mechanism. And these registers that we have made use of, they are called memory mapped device registers. Why? Because these registers, every register will have an address. Keep this in mind. So every device register, every register has an address, and this address is assumed to be same as a memory address. So it is like you write the address, use the instructions to provide an address, but that address will not be a memory address, but it will be one of the registers of the I/O. So you may wonder, how do I get to know about the register? Well, you have to consult that device, the data sheet of that particular device controller, and there the vendors of they provide you the address of each of those registers. Okay. The processor is responsible for transferring data to and from the device by writing and reading to these registers. Good. What next? It's a very pertinent question. We just saw that there are three kinds of registers: status, command, data. Now, how do I know that that particular device is ready? How do I know that? Now, we need to know that whether the device is ready or not. Because when the device is ready, then it will be accepting a new command. Right? Because until the device is ready, it will not get new command. So how will you know that? Now, there are two ways to do it. One is called polling. What is that? Well, polling means we've already seen the same concept when we were discussing about semaphores. Anyone remembers that? The busy loop problem. What is it? What is the concept of polling that we discussed? Anyone who remembers it? What is the concept of polling? Polling means you constantly check whether the device has become ready or not. Okay, so you constantly check whether the device is now free to be sent some command. Suppose a process is currently using a printer. So the printer is printing something. So if the printer is printing, the other process cannot send, right? So what will happen to the second process? It will be looping. So during the loop mechanism, what will it check? What will the second process check? The status of the printer. So the second process will always be checking the status of the printer. Let me give you an example. You are reading a book and you have turned your mobile into in silent mode, and even your vibrator is not working correctly, and you are expecting a call. So every 5 minutes, you keep on checking whether somebody has called you on. So that's polling. You stop your work after some time and you check whether you are expecting the call. So this is the idea of polling, and this is the way in which you may, or the CPU may find out, okay, that this device is now ready. You have to constantly, periodically check whether it is ready or not. Is that a good way to do? No. Why? Because you are constantly wasting cycles. Let me give you an example through this diagram. Okay, here you are. Let's first look at, so this is the diagram. Are you able to see this? Students?
Yes, sir.
Yeah, okay. Let's look at the first figure. Okay. This is the 111 that you see here. Let us assume that process 1 is running on the CPU for some time, which is indicated by the repeated 1 on the CPU. And after this 5 time slices, let us say there is an IO request to the device. That's an IO request to the disk to read some data. Okay. Now let us assume that when this IO request is there, there is no other mechanism. So what happens is the disk will serve the request and process 1 will run again. Now think about the situation when the time the disk was reading that particular file. What was the status of the CPU? What was the CPU doing? CPU is waiting. So for this 5 time slices, which is shown by P, the disk is performing some operation. It is reading the data, 1, 1, 1, 1. So during the time, CPU is keeping quiet, right? CPU is keeping quiet. And we have just seen in the chapter on process synchronization, to avoid CPU unnecessarily sitting idle, we allow CPU to run the process P2. So during the time when CPU process 1 was performing a file read and the disk was operating, CPU was executing process 2, which is shown in the next figure by filling up those spaces by 2222. It is like the OS now is running process 2. So interestingly, both the devices, the CPU as well as the IO, are utilized. This is utilized. But the question is, when the process 2 was running, it was constantly, there was also constantly a check that suppose there would not happen any interrupt. Okay, there was no interrupt. Let's talk about the first situation. You know that the disk is currently completing, there's one process. Until that is completed its task, second process would not have been given a chance. So until the disk completely reads the the file, the first process will the second process will constantly be checking whether it is free, whether it is free or not. This is the drawback of this coding mechanism. And the second one, where you see that I don't care about whether the disk, whether process 1 has completed or not. Process 1, let that be in the IO request phase, and during the time the CPU now is becoming busy with process P2, and when it is running process P2, it is interested only in running process P2, and is now doesn't need to check the status of the process P1 or the device controller. Why? Because when the device controller will complete its task, when the device will complete its task, it will automatically inform CPU that my job is over. How? The line through which that particular CPU will be told is called interrupt. So every CPU we know is having an interrupt line. So what happens is, once P1 has finished reading the file, it will inform through the interrupt that my job is over. So the unnecessary looping cycles, which was a waste in the polling concept, is overcome by the user. Clear? This is what we have as the two ways in which the IO can communicate with the host. Well, there is one more very interesting mechanism of data transfer, and this is specifically when you want to transfer bulk data, and this is called DMA. DMA stands for direct memory access. And let's look at the situation. Look at the diagram. Is it visible to all of you? Is it visible to all of you, the diagram? Okay, let's look at the diagram. The first one, the top, the figure on the top, which is showing some operations of the CPU. The one which is the string of ones that you see is the process 1 running on the CPU. Okay. And after these 5 ones, you have a string of small c. This small c is a copy operation. Let us assume that process 1 has to copy something from the disk. It has to bring some file from the disk. Bringing file means some copying operation from the disk. That means an IO request. The moment this IO request is there, it is taken out and another process is given a chance, which is process 2, which is shown by the string of 2s. So now CPU is currently running process 2 and the disk is running the process 1, not process 1, actually the file required by process 1. This is what happens. Fine. So what is this DMA? Well, the interesting thing to be noted here is the moment you see some kind of operation like a bulk data to be transferred from the disk, this will take a lot of time. And this operation is same kind of operation which is done very, very slowly. Why? Because the disk is a mechanical device and that transfers data very slowly to the CPU. Effectively, the CPU is doing no computation. It's a very, very stale job, which is like copying blocks of data from the disk to the memory. This is what we are doing. Now, this kind of operation, if the CPU does, it is spending a lot of time doing unnecessary tasks. And that is bringing down the performance of the system. So a better approach to improve the performance is that the moment the CPU sees, oh, process 1 needs some data to be transferred from the disk to the memory, the CPU says, well, I am not going to do it. there is another hardware which is called a DMA controller. What is DMA? Direct memory access. DMA engine, you may call it, DMA controller, you may call it. So what CPU says is, please take care of this operation. So look at the diagram now, which has been shown. The first string of ones, okay, they were running on the CPU, which is process 1. But the moment process 1 goes into a copy operation from the disk, CPU just initiates or triggers the DMA controller, and now the DMA controller starts sending the copy instruction to the memory. Memory means the secondary storage, the hard disk. And the transfer now is controlled by the DMA. What happens to CPU then? Well, CPU can run any other process. It doesn't have to wait for the entire file operation to be complete and then it will start. It can do some other work. So look at how this DMA becomes very, very helpful. Whenever you have a huge amount of data to be transferred from the hard disk to the memory, when do you have this situation? When you read a file, let's say it's a very big file. Suppose you want to execute a movie, a 1 GB file. You are going to play that. It's residing on your hard disk. It will take a lot of time. So who will do all that? Well, the CPU will just initiate the process. When it is working with the file, fine. But when it sees that, okay, I have to bring a lot of blocks of data from the hard disk to the memory, I have to load that. It does not do it. It passes on that control to the DMA controller, and it itself goes into executing some other process. And in the background, the DMA controller is sending out instructions to the hard disk and getting the data from the hard disk to the memory. And that is the reason why it is called direct memory access. Direct means it is not, there is no CPU involved in that. CPU was there. Usually what happens? When we bring something from the hard disk, we first bring it into the CPU, one of the CPU registers, and then we transfer it to the primary memory. This is what happens. We just saw in input-output device. What happened? You sent out an instruction, you got it from the data line of the hard device controller to the CPU register, and from the CPU register, you send it to the memory. This is how things happen. But if you bring so many blocks of data and bring them one by one into the CPU register and then from CPU register to the memory, and this is how you transfer data, it will take a lot of time. Better you involve somebody else that will receive the data from the hard disk and directly transfer it to the memory. This is called direct memory access. This is another mechanism by which the performance will be improved. Okay. Is that clear, everyone? The concept of DMA? If you have any problem, please feel free to ask me, because it's very important for all of you to understand these very, very basic or very fundamental ideas. Because when I'll be talking about files, if you don't understand them, it will become very confusing. Is that picture clear now? What is lying below? What is at the hardware level? Everyone? Yeah. What one of the answers? Any questions if you have? I'll stop here for some time to take any question if you have. No? Okay. Okay, so if you don't have any questions, then we can move on to the next.
Sir, what is namespace?
Okay, namespace is the way of naming different files and directories. We will talk about that in more details in the upcoming lectures. So it is just the way in which you provide names to the different files and directories. Okay, in which you organize the names. Is this lower level is it clear, the concept?
Yes, sir.
Okay. Now it's a very, very pertinent question. The final problem is, how do you fit these devices into the OS? We understood every device has its own controller. They interact with the CPU, whether it is through polling or through interrupt or through DMA, whatever. Ultimately, that particular controller has to be programmed. Now the problem is that every device has its own way of working, and there are several devices. How will you fit these devices into the OS? We go back to the same answer, abstraction. There may be so many devices, we don't care about that. The solution that we have is the operating system would have an abstraction layer for every device. And this piece of software that provides this abstraction is called device driver. Let us now look at what a device driver. How many of you are aware of this term? How many of you are aware of this term? Have you heard of this term earlier? Yes, Pankaj says. How many of you heard of this term? When do you use it? Anyone who has? When do you use this?
So it is part of OS.
Part of OS, that's fine. But suppose tomorrow I bring a new device, say a camcorder. I purchase a camcorder and I connect it to my Windows machine. What is the thing that I should do before I can record or read that particular device? What should I do?
We will have to first make sure that our Windows supports that particular hardware device or not.
Good. What else?
And there should be proper API interfaces in our .inf files or .sys files that Windows uses to communicate with that particular
Have you
device.
seen that every device that comes with a, used to come with a DVD, a small DVD or a small pen drive? Yeah, so Abhi says that it requires drivers. What are the drivers? Have you seen that every device comes with a DVD, small DVD or a small pen drive, and it says that you first plug into that, and usually it's an auto run which automatically loads that piece of software. What is that piece of software that usually the vendors provide for working with that device? It's called the device driver. It's that piece of code, that system interface, which gets loaded onto the kernel, so that the kernel now recognizes that particular device and it recognizes the commands that must be sent to that device so that the device can be read or written. That is called the device driver. Simplistically put, it is a software in the kernel that interfaces with the device. You must have by this time understood the hierarchy. The hierarchy is device, hardware controller, operating system, CPU. Okay, so here it is, like we have the device, the hardware controller of the device, which is a chip. Sitting on top of that, there's an, so this till this part is the hardware. Now we have an application that is running. The application will be needing this device. What is in between? So here we have on the OS side, here we have the CPU, And on the app side, we have the OS or the kernel. So the app would be putting the request to the OS via some system call. And that system call in turn would be transferred to the hardware controller and finally to the device to provide the data. So there must be some kind of interface, but every device will have its own hardware controller and own way of communicating or own way of data transmission. So how will the kernel know which device, what is its command? So this device and its controller must be registered within the kernel. It must provide some interface. Okay, that is what we call the device driver. Look at that. So because there is, again, there can be another hardware controller and device D2, then there can be another hardware and this hardware controller and device D3. So they are individual, but this is a common interface. So this is a common interface where the app would be requesting the OS. That's common, the list of system calls. But these are individual. Now, how will this OS kernel talk to this one, each one of them? Each one will have its own custom way to talk to the kernel. And this piece of software that you have to put so that this controller can talk to the kernel is its device driver. That is why it is called a custom interface. It's specific to that particular device. So it's a piece of software that allows the kernel to interface with that particular device. Device means the device control. And I said device, I will not mean that literally the device control. So the device would be interacted with the kernel or interact with the kernel via this device driver. Okay. The device system. What do you have in the device? I already have told you about that. We have some buffer cache and the IO scheduler, some generic device driver code, and driver for specific devices. This is what you have inside a device driver. And majority of the maximum OS code is nothing but the device driver. If you look at the total lines of code of a kernel, you will find that 80% of that is occupied by a device driver. Okay. What is that makes up a device driver? Some IO scheduler, some generic device driver code, and some driver for specific drivers. That's what makes up the device system, the bundle of device drivers which is maintained by the kernel. That's what forms the device driver part of the kernel. What is the role of the device driver? It is an implementation mechanism. What does it implement? Well, some mechanism to interact with the device. You have a keyboard, you need a device driver for a keyboard. So that's a piece of software that allows your Windows operating system to detect that particular device and to interact with that particular device. Okay. Now, device drivers can be compiled into the kernel. For example, there are a lot of device drivers that are already available when you install the Linux kernel. You don't have to install any specific device driver. They are pre-compiled into the kernel. They're already there. Okay. Or you can load them as modules that you normally do when you install a device driver into your Windows operating system. Okay. That DVD that you play, that auto runs and then installs the device driver so that you can work with your device. So the kernel modules, the chunks of code that can be loaded and unloaded into the kernel on demand. We just saw that device drivers can be loaded as modules. They are called modules because they can be loaded or unloaded. It's a dynamic loader, okay, which links unresolved symbols to symbol table of the running kernel. We'll talk about that later on. For the time being, just keep this in mind. There are a lot of modules which are loaded during runtime. They're not pre-compiled. For Linux, we have the install module if you would like to add some module, or the remove module if you would like to remove some. Module underscore init, which each module has a function that the kernel calls to initialize the module. This is like initializing a particular. It is how you add or remove that. I'm talking about the lower level kernel related commands, which allows you to add a module, remove a module. Okay. And then as you see here, kernel keeps a use count for each device. Okay. Whenever you have the use count equal to 0, it means there is no device currently attached. As you keep on adding, the use count is implemented. This is very important. The device driver. When you are using a device driver or a device that is a device driver which is not pre-compiled, you are adding that to the kernel as a module. That module has to register itself. And it is important. Why? Because until the module, the one that is added, until it registers itself, how would the kernel know? And that's very important. But how will the kernel know that there is one module that has been added? Have you seen device registry in your Windows operating system? How many of you have looked at this? Anyone who has seen the device registry? Have you opened that ever? Okay, here is one. Mithu. Anyone else? Have you explored your Windows operating system? No. Okay, so today all of you must go and have a look at the Windows registry. Look at that and see the devices that have registered themselves. Let's look. So device drivers, they register themselves as devices. Very important. The device drivers, they register themselves as devices. Take for example, if you are attaching a character device, okay, it's a character driver. So it initializes as a CDEV. It's a structure, and then it implements the file operations. If it is a block device, it will be written as gendisk. It's again a generic disk structure, and then we'll implement block operations. Network device, it will register as a network device structure and implement as a net device. Okay, I've already told about that, so there's nothing much to discuss. I'll just simply skip this. Okay, I'll move towards now very, very important part, which is we'll finish off this lecture with the discussion about these devices. Now here is, we told that the device system, the device driver system, it consists of device drivers, some buffer cache, etc. What is this buffer cache? I'll come back to this in more details in the last part of this chapter. So for the time being, let me introduce you. What is buffer cache? Well, it's a pool of kernel memory to hold frequently used blocks. You must have by this time understood that when we deal with block devices, let's say a hard disk. What is this hard disk? Well, the hard disk is, it's a block device, right? It's a block device. So your data is present in the form of blocks. Let me give you an idea so that you understand it. If you look at the hard disk, it is like, as the name is, it's a disk. Okay? It's a platter structure. And this platter has an concentric circles. They are called tracks. They're called tracks. And these tracks are divided into different sectors. It is like this. Okay. So this is called a sector. This is called a sector. So you may think this is a block. And how are these disks arranged? Well, the disk is arranged in this way. Here you have this concentric circles, and here is something called a head, right? It's a head that is there. So this head, it moves laterally in this way. So it moves this way. Okay, this is how it moves. And this disk, it rotates in this way. Okay, so it rotates circularly, and this moves this laterally. So you see, when the head moves, there is one of the sector that comes below the head. And the sector that comes below the head, it reads the data from there. So the sector that comes below the head, this is moving this way, and this is moving in this way. So it is actually covering all the tracks, and this is moving in and moving along all the sectors. So whenever there's a particular sector that comes just below the head, it reads that entire block of data. That entire block. Right? So let us assume that I have to read a file. Now, what is this file? File is an array of bytes. Please listen to this very carefully. Suppose my array of bytes is, let's say, 1 MB size file. Okay. Now, this 1 MB size file is divided into number of 512 byte blocks. Let's say some n number of 512 byte blocks have been created for this 1 MB file. Okay. Interestingly, this 512 byte blocks, so this 1 MB file is equivalent to how many? 1 MB is to the power 20, and 512 is what? 2 to the power how much? 512 2 to the power 9, right? So it's like 2 to the power 11. 2 to the power 11 blocks we have. Now these 2 to the power 11 blocks will be distributed all through this hard disk, right? All through this hard disk they will be distributed. And then you have to send this blocks one by one. Block number 0, block number 5, block number 7, block number 6, 7, and 11, 152. In this way, you will be sending out one by one the block numbers. And they will be accessed one by one, and the entire block will be obtained. All the blocks one by one will be obtained, and the entire file is read. This is how a file will be read. Now, it may so happen that during that entire file reading, some blocks are read very frequently, like 0, 5, 5, 5, 5, 5. After some time, is 6, 6, 6, 6. These blocks are frequent. They don't not necessarily has to be different blocks. They may be the same blocks which are repeatedly accessed. Now, if you see that a particular block is repeatedly accessed, is it really required to read it from the disk every time? Because what will you do? You will read that data of the block, you will put it in the memory, and then the CPU will read it from the memory. This is what you will do. So every time if you have, let's say, 20 block number 5 you have to read, is it really necessary that you go to the disk every time and then read that same block? Can we not have a better approach than that? A caching approach? Can we not keep a pool of the repeatedly accessed blocks? And when I have read it for the first time, I keep it in the cache, because next time when I will be reading it, I don't have to go to the disk and read. I will be getting it in the buffer cache. Why? Well, reading from the disk is a slow process. So I will be getting it in the buffer cache. So that is the idea here of you keep a pool in the kernel. It's a kernel memory. You keep it and you hold the frequently used blocks. So what do you do with that? What do you say? You minimize the number of IO requests. Okay, this is the advantage that you have. And that is the reason why buffer cache is used. Look at the diagram that has been shown below. The user IO request first look in the buffer cache. If it is not found in the buffer cache, then it goes to a device block IO request and then finally to the device. This is the structure. Clear, everyone? The requirement of buffer cache? Fine. So the buffer cache interacts with the underlying block device, and options to the user is the system called them. Now there are two kinds of IOs. One is called the blocking IO and the non-blocking. Blocking means until the user process completes the IO will be blocked. It's not used. Okay. Non-blocking means you schedule the output, but don't wait for it to complete. You don't care about that. You don't care about that particular output to be happening. You don't care when the file transfer will be happening. You just initiate the process, let the output be done, and then you go on to do something else. Okay. Yeah. So another class of IO that we have is asynchronous, which is your request will return immediately, but the IO will be scheduled and the process will be signaled when it is ready. So you have made an IO request, but it is not immediately given to you. It will be put in a schedule, that is, will be put in the queue, but will be provided only when it is ready. Okay. So this, one of the advantages of having this is to minimize the data loss. We'll talk about that later on. Okay, so buffered is already, we discussed about that. As I think file system, I'm not talking about today because this is going to come in a big way in the next class. So I'll, for the time being, omitting this. Yeah, character device and all this. So let me go to, yes. So what is this device driver entry point? This device driver, it provides a fixed set of entry points, which is whether the device has a block or a character interface. The block device interfaces appear in the block device table, and the character device interfaces, they exist in the character device table. It's just two tables that are maintained, depending on whether you are handling a block device or a character device. And then the device is handled in the form of a major number and the minor number, as you see here. Major number is, it identifies the device from the device table, and minor number is, it interprets it within the device type. Because there can be many devices, right? Suppose the application wants a particular device. It has requested for some monitor. It's a graphics controller. So there's a device which is there. First, you have to understand what kind of a device is being asked. Is it a block device or a character device? Accordingly, you will look up to that particular table. Once you have looked up to that particular table, then you know that there are a lot of character devices. Which character device? So this will now help you in identifying that particular device. Now somebody was asking me, what is this namespace? So here is one of an example, though it's not exactly, but okay. What is it? This is how you locate a device. So you have an explicit namespace, which is called the MS-DOS approach. You already have seen that, isn't it? When you install or when you work with a particular drive, you see these letters coming up very often in your Windows system. C, D, you call them as C drive, D drive. What are they? they are some portions of your hard disk, some partitions as they are. Your hard disk, which is a permanent storage, has been divided into number of volumes or segments. You call them partitions. Details of that will come later, how we read that, etc. And every partition has a specific way of storing files. Okay? That's called the file system. Windows uses a file system called NTFS. We'll talk about that in the next class. So these are the partitions, and these partitions are identified by a specific name. That's called the namespace. LPT, usually used for the printers, the parallel port. COM1, the serial port. So these are very common, names that are used to identify a particular device. What is the idea behind this? The idea is that you use a file system interface as an abstract interface for both file and device. That's the logic behind using the name for a device. See, look at this line. This is the most important line, and you can say the summary of our discussion. Whenever you are having a device, an IO device, you treat that as a file with no content, but only metadata. Okay. What do you have in the metadata? What do you have in the file that corresponds to a device? You have the file type of the device, the major and the minor numbers. That's what you have. The devices are traditionally located in the /dev. I'm talking about a Unix-based system. So they are usually present in the /dev. Okay. So if I can show you the terminal, so all those who are on a Unix-based system, open up a terminal and just type in ls/dev. You will find the list of all the devices that you have in your system. They are identified as files. Okay, and they are created by the mknode system. Let me end up this with so device names. Windows uses, when a device driver is loaded, it is registered by the name object manager, and names have a hierarchical namespace which is maintained by the object manager. As you see here, Windows uses something like device serial 0 / device CD-ROM 0. It's a common difference between Windows and Linux is that Windows uses a backslash to differentiate, and Linux uses a forward slash. So the Windows NT architecture, that's like XP 2000, they use this kind of, it uses an object manager that keeps track of all these devices. And Win32 API that requires MS-DOS names, like with Windows 32 programs. And the same thing, if you look at the Linux, it uses the /dev, like static devices with the mknode. And we have the kernel here. This is the device. And these are the different utilities that are used for performing or for accessing or for creating the devices within the /dev tail. So static devices, the mknode utility, and the kernel device manager is udev, which is a user level process. So since we've seen that devices are also handled as files, we have character devices that include these entry points. Look at the way in which they work, very similar to how files are handled. Open, close, same commands that you use for files can be used for handling devices. So we'll show some example. Yeah, this is what you see. Let's look at this example. Suppose there's an IO request which is received. Okay, so the request is placed on a per device queue. This is the device table. Look at the diagram. Device keyboard status idle, devices disk 1 status idle, device disk 2 status busy. So whenever an IO request is received, you first look up to the device status table, which contains the list of devices and their status. And each one of them has an IO queue attached to that. For example, you see device disk 2. What is the operation? Read. Which block? This block. This is the starting block. What is the length? This is the length of the block that should be read. Address here. Then what is the next operation that should be done? Write operation. Which block? 1204. Length 4096, and this is the address. So there's a status table maintained of the device, and each one of them will have a list of an IO queue which contains the information about the different operations, the block that has to be read. And so this is the mechanism by which the kernel interacts with the. So I'll stop it here today, and tomorrow we'll take up the structure of the IO devices, which will basically be focusing on the hard disk. We'll talk about the structure of hard disk and the different IO scheduling techniques. So let me quickly summarize what we learned today. Today we discussed about the different IO data transfer mechanisms between the CPU and the IO devices. We learned about the different type of IO devices. They can either be character type, block, or network type. We saw how devices communicate with the CPU. Every device, whether it is block, character, or network, has a device controller, which is nothing but a collection of registers and some complex circuitry that actually acts as an interface between the CPU and the device. So if the device has to be accessed by the CPU, that device controller has to be programmed. Specifically, the registers, which are status, command, and data, they are the ones that are utilized. The status register is read by the CPU to find out the status of that particular device. Then a command is sent to the command register. The command is either read or write. And finally, the data is transferred. Either it is read from the data register to the CPU, or the CPU sends it to the data. There are three different ways by which the status is checked. It is either done through polling, where constantly the status is checked to see whether it is free or not. The second option is whenever there's an IO request, the CPU moves to execute some other process. And when the previous IO request is complete, the device itself mentions it to the CPU that it is done, and this is called interrupt. In addition to that, there is one more way of improving performance, which is called DMA mode, where the CPU is not used in the picture. There's a device which handles the data transfer between the device and the memory. Then we said that that's on the hardware side. How does the kernel know about all this device? The kernel uses an interface, a software interface, a piece of software, which is called the device driver, which is an interface that allows the operating system to identify the device. And the device is identified, the device has to register itself in the, and all the device controller information is mentioned in the device driver. Then we also saw an example, typical example of the device driver, way of how the IO is handled in case of how the IO interacts in case of a Windows-based system and a Linux-based system. Now that we are clear about the lower level interaction between the hardware and the kernel, the next step is, okay, how do these blocks accessed we saw that, okay, 1 MB size of file is equivalent to, let's say, 2 to the power 11 number of blocks. So this 2 to the power 11 number of blocks have to be accessed one by one. The block numbers have to be provided as an instruction. How will we access those blocks? That's what we are going to see tomorrow. And then we are going to see, well, this is what is seen by or is happening at the lower side. The application doesn't understand that. What does the application understand? It understands something called a file, which is an array of bytes. So tomorrow we are going to see how this array of bytes gets translated into a number of blocks. And then we will gradually go into the file system level, where we'll see how files, what are files, how are files managed, how are the different operations of file, and we'll talk about different file management techniques, file implementation techniques. We'll talk about the NTFS file system, the FAT32, the Linux ext3, and we'll talk about different operations such as mounting an operation, virtual file system. So this is the concepts that are going to come in the subsequent lectures. Okay, so this is all about today.